Hello everyone, I'm Jeon. I'm a graduate student at Purdue University. In this presentation, I want to introduce you to Fuzzan effective sanitizer metadata design for fuzzing. This is a joint work with WookHyun from KAIST, Burow from Purdue, and my advisor Mathias. Before introducing Fuzzan's motivation, I will briefly explain sanitizer and fuzzing. First, a sanitizer is a debug tool to detect policy violations. More specifically, sanitizers observe the actual execution and they flag incorrect behavior. Until now, a vast number of the sanitizers have been prototyped by academics and refined by practitioners. For example, address sanitizer, memory sanitizer, sanitizer, and undefined behavior sanitizer are widely used and LLVM support sanitizers. Among these sanitizers, we mainly focused on address sanitizer as address sanitizer is most widely used sanitizer. Address sanitizer focused on detecting memory safety violation. For instance, let's assume that this is process memory. To detect a violation, address sanitizer insert red zone between allocated objects and use the shadow memory to record whether each byte is accessible. Then, if program access this red zone during an execution, like invalid address P, address sanitizer can detect memory errors. So far, Address Sanitizer has detected more than 10,000 memory safety violations. Next, let me talk about fuzzing. Fuzzing is an automated software testing technique. During fuzzing, the fuzzer generated random inputs and it received the feedback from the test program. Based on this received feedback, the fuzzer continuously generated inputs and then it tests application with these generated inputs. During this repetition, when the target program causes segment fault errors, the fuzzer can detect bugs. However, all bugs cannot cause segment fault errors immediately. So to detect triggered bugs, the fuzzer usually leverages the sanitizers. For instance, we analyzed Google's fuzzing bug report and found that address sanitizer contributed to finding 42% of them. Like this, combining a fuzzer with a sanitizer is an effective and popular choice. However, we found that sanitizer is not optimized for the fuzzing environment, which can have highly repetitive and short execution time. For example, when you adopted address sanitizer, it increased the fuzzing performance overhead about 7 times. This means although the combination of fuzzer and address sanitizer can detect triggered memory corruption bugs, it will take longer. We further analyzed this high overhead and they found 3 major costs. The first cost was an increased memory management overhead. More specifically, address sanitizer reserved a large virtual memory area and address sanitizer accesses these areas for metadata accessing or logging, meaning that accessing the untouched memory by address sanitizer cause page fault and uh, required additional overhead to allocate and fill out the corresponding page tables. Additionally, when the process exits, the kernel needs to clear all page table entries and release a memory for the page table. Also, address sanitizers a large memory area cause sparse page table entry. Therefore, according to our evaluation, after applying the address sanitizer, the page fault were increased by 365%, and the memory management time was also increased by more than 1,000%. Also, we found a considerable overhead from address sanitizers, initialization, and logging functions. We found that these overheads are avoidable through Fuzzan. In Fuzzan, we proposed 4 different approaches to address this high overhead issue. First, we propose the multiple lightweight metadata structure instead of Address Sanitizer's heavy shadow memory. In the lightweight metadata structure with compact memory space, we prevent a sparse page table entry, and therefore we can reduce memory management overhead. Also, each metadata structure is optimal in different circumstances. So this motivated our dynamic metadata structure switching mode. I will report this dynamic switching mode from this point on. So considering the fuzzing environment, the target program behavior can be changed according to the mutated inputs. Therefore, we propose the dynamic switching mode to profile at runtime and switch to selected optimal metadata structure. Finally, we removed Address Sanitizer's avoidable logging and initialization overhead. What you see here is the Fuzzan's overall design. Instead of Address Sanitizer's heavy shadow memory, we propose the three different modes, including two lightweight metadata structure modes. During fuzzing, we periodically run our Fuzzan sampling mode and measured the target program behavior. And based on feedback, we calculated the optimal metadata structure and switched it to the selected metadata structure. During fuzzing, we periodically repeated this process to increase the fuzzing throughput. Now let me show you two new Fuzzan's metadata structures, arbitrary and mean shadow mode. First, we design arbitrary for target application with a few metadata access. Since a corresponding arbitrary size and the memory management cost can be small, but metadata access cost will have to be high. In the case of the mean shadow mode, this mode is based on Address Sanitizer's shadow memory. As Address Sanitizer map the target application's address space into the shadow memory, to maintain a corresponding compact shadow memory, we forcibly shrink application's memory space. Therefore, mean shadow mode has a lower memory management cost than Address Sanitizer while keeping the same metadata access cost. So mean shadow mode is designed for target application with frequent metadata access. So let's talk more about mean shadow mode. On the 64-bit platform, the Address Sanitizer enabled programs has the shown memory layout. Then all segments are mapped to 16 terabyte shadow memory area, including the 4 terabyte in memory. Address Sanitizer enabled program reserved more than 20 terabyte of shadow memory. As we discussed before, we shrunk application's memory space to maintain corresponding compact shadow memory. For example, if we shrink the target application's memory space to 4 gigabytes, we only need to maintain around 500 megabytes of shadow memory. So even with the heap, we only need to reserve 1.5 gigs of space. Therefore, compared to Address Sanitizer, we reserved significantly less memory space. Additionally, each program has a different heap memory requirement. To support this, we created a different mean shadow mode, which has different heap memory sizes. However, as no single metadata structure is best for all locations, we propose the dynamic switching mode. To be more exact, there are three main reasons. First, dynamic switching mode automatically select optimal metadata structure. So this saves time and effort of the user. More specifically, as I mentioned before, no single metadata structure is optimal across all applications. For example, arbitrary showed best performance when the target application allocated few objects. Therefore, without dynamic switching, the user has to spend their time to calculate the optimal metadata structure. Second, dynamic switching mode dynamically change the metadata structure according to the target's behavior. To be more exact, under the fuzzing test, the Program's behavior can be changed based on the mutated inputs. So we need to profile at runtime and switch to selected optimal metadata structure. Last, if the target application exceeds the current most heap memory limit, we need to automatically increase the heap size. For this dynamic switching mode, we thought about measuring target applications' current behavior periodically. So we designed sampling mode that extract target program's behavior, such as the metadata access count and heap object allocation size with the current mutated input. Also, sampling mode maintain the same detection capability as Address Sanitizer to not miss any bugs during sampling. Next, I'm going to introduce our additional effort to address Address Sanitizer's initialization and logging overhead. To remove Address Sanitizer's initialization overhead, we use the focus server to avoid unnecessary initialization, such as poisoning of global variable. To understand this differ, the fuzzer generally use a focus server to improve the performance. So fuzzer set an entry point after the most things are initialized. Unfortunately, the fuzzer's focus server remains unaware of Address Sanitizer. So our solution was to move Address Sanitizer's initialization point to before the focus server's entry point. Also, to remove logging overhead, we modified Address Sanitizer to disable the logging functionality. This is because, luckily, Fuzzing can easily replay the bug by using the stored test inputs. So Address Sanitizer does not need to record logging during fuzzing, as complete logging can be recovered with the full Address Sanitizer later. And now, let me show Fuzzan's evaluation result. First, I would like to demonstrate Fuzzan's detection capability. This is necessary because we replaced Address Sanitizer's metadata structure. To prove this, we tested Fuzzan's different modes with the Juliet test suite, Address Sanitizer unit test, and the Google Photo test suite. During this test, we confirmed that Fuzzan's detection is just as good as Address Sanitizer without any false positive and false negative. We also took a look at the performance of Fuzzan's new metadata structures. This graph compares native Address Sanitizer, Fuzzan's arbitrary, and Fuzzan's 4-min shadow memory mode execution overhead with provide seed set. For this evaluation, we conducted input record replay fuzzing to ensure the fair comparison. The time indicate the average of all 26 Google Photo Test Suite applications execution time during fuzzing. In the case of Fuzzan's arbitrary, on average, performance was around 200% worse than other sanitizers. Because some specific applications show higher overhead compared to other sanitizer. But the Fuzzan arbitrary can be faster on individual applications. For instance, arbitrary mode showed the performance up to 39% better than other sanitizer for 14 applications among the 26. In the case of the min shadow mode, it outperformed other sanitizer on all 26 applications, even while different min shadow mode if configurations showed gradual overhead increases. And we also compared the performance of remove logging and initialization overhead and dynamic switching mode. This graph compares the native Address Sanitizer and Fuzzan 6 different modes of execution overhead during all 26 applications input record replay fuzzing with provide seed set. First, the average of improvement of removing unnecessary logging was 90%, and similarly, modifying the initialize the scales of improved performance by 11%. And also combining the two optimization improved performance even better by 25%. And combining two optimization with the mean shadow memory showed 5% better performance than native mean shadow mode alone. Also, Fusion's dynamic switching mode performance exceeds ordinary sanitizers by 48%. Although dynamic switching mode has an identical fuzzing performance to using 1 gig's mean shadow mode, dynamic switching mode is needed. To be more exact, this figure shows why dynamic switching mode is needed. First, we evaluated the frequency of the metadata structure switching and each metadata structure selection over the first 500,000 tests. The number on each bar indicates the total number of the total of the metadata switches. First, dynamic metadata structure switching automatically select the optimal metadata structure. For instance, these applications in the box were dominated by different metadata structures. For example, CARES for arbitrary and the PNG fix for mean shadow memory. Therefore, without any user effort, dynamic switching mode automatically selects the optimal metadata structure. Second, dynamic switching mode scale alongside the required memory of allocations, as evidenced by size or NM applications switching to different mean shadow modes without without the user intervention. Based on all these results, here is the detailed explanation for why Fuzzan performed better than Address Sanitizer. And you can see this with perf overhead analysis result. This result is aggregated over 500,000 executions of the full Google for the test suite. We can see 2 points here. First, like a mean shadow mode, the smaller memory space of our metadata structure reduced memory management overhead around 60%. And since the page table management was more lightweight and incurred the fewer page table faults around 40%. And second, like a two optimization with the mean shadow memory mode, our two optimization further reduced the overhead and reduced the number of the page fault by around 60% by removing unnecessary operations. Because of this, when the tester selects Fuzzan instead of the Address Sanitizer, it will help to find bugs more faster given the same amount of the time. To demonstrate this, we evaluated Fuzzan's bug finding speed and compared it to a Fuzzing campaign with the Address Sanitizer. In this evaluation, we target 5 applications in Google's Fuzz test suite. We chose these applications because we found these bugs within 24 hours of Fuzzing campaign. We used the provide seed set and repeated each campaign 5 times. We also did not replay record input during these campaigns. As a result, Fuzzan found all bugs up to 61% faster than Address Sanitizer and was faster in all cases. This experiment emphasized our belief that throughput is paramount when fuzzing with sanitizers. We also evaluated Fuzzan using the standard 24-hour fuzzing with widely used 7 real-world softwares and the right time file seed. And we used the Address Sanitizer and Fuzzan dynamic switching mode for this evaluation. Each campaign was conducted for 24 hours and repeated 5 times. We measured the number of the total executions and discovered unique paths and report the mean over the 5 campaigns. As a result, the Fuzzan had a better throughput over Address Sanitizer by 61%. Fuzzan discovered a 30% more unique paths within the same 24 hours because of improved throughput. To wrap up, Combining a fuzzer with a sanitizer is a popular and effective method. However, this combination is limited by high performance overhead. To address this available issue of high performance overhead, we propose the Fuzzan. In the Fuzzan, we propose the novel metadata structures, dynamic switching mode, and we removed unnecessary operations. Our evaluation showed that Fuzzan improved the fuzzing throughput by 48%, starting with provide seed. It describes 30% more unique paths than Address Sanitizer. And it also provides flexibility to other sanitizers and AFL-based fuzzers. The open source version of our Fuzzan is available at this link. This concludes my presentation. Thank you for listening. I would be happy to take your questions.